Welcome back. So today we're going to start a new part of the course and we'll talk about a new model of computation called PRAM. So we're going to spend the next few lectures on PRAM, and today we're first of all going to introduce the PRAM model and then talk about some basic algorithms. All right, now PRAM stands for for parallel random access machine. Okay, and this PRAM model is basically meant to generalize the normal model for sequential computing, and that is the von Neumann model. Okay, so if you remember, the von Neumann model is actually very simple. So we have a CPU, and then we have a memory, right? And the CPU can talk with the memory. So then in the von Neumann model, in every time step, the CPU is going to read some data from the memory, right? And then it's going to do some computation on that data, and then it's going to write that data back. Okay, so that's one cycle of what the CPU does, and then the CPU just repeats these cycles over and over. Right, now in the PRAM model, we're simply going to generalize this into the parallel setting. And the way we do that is just that we're going to have multiple CPUs. Okay, so we have now a parallel computer with multiple CPUs, and in every time step, these multiple CPUs can altogether, they can in parallel talk to the memory. Okay, so each CPU can access a different part of memory, can read from a different part of memory. Okay, and then the CPUs can each do a computation. Okay, and they do that all in parallel. And then they're going to write something back to memory. Okay, so every CPU is going to in parallel write something possibly different back to memory. Okay, and so that is now going to be a cycle of the PRAM computation, and these CPUs that we have are just going to repeat these cycles over and over. Okay, so now the question, one question is, how many CPUs are we going to use? Okay, and the number of CPUs we use can actually depend on the size of the problem we're solving. So for example, if we're solving if we're, let's say we're trying to sort n numbers, okay, then we're allowed to use f of m processors for some function f that we select. Okay, so maybe we want to use square root of m processors, or maybe we want to use n log n number processors. Okay, so we get to select how many processors we want to use. And f of n can actually be very large compared to n. Okay, so for example, if you're sorting, let's say, a million numbers, okay, in the PRAM model, you're allowed to use 1 million processors. Okay, you're even allowed to use more than 1 million processors. Okay. All right. Yeah. So then this here just says what I was. So it describes the model I was mentioning, right? So these processors are all synchronized, by the way. All right. So every time step, all of the processors are going to read from the memory, right, in synchrony. Okay, they can read from different locations, but all of them are going to read. Okay, and then and then all of them are going to compute. Okay, in synchrony. Okay, and then all of them are going to write back. Yeah, so this is a little bit like the SIMD model that we talked about, right? The single instruction multiple data, or except for here, the different CPUs can do different instructions. So it's not single instruction, they can each do different instructions. Okay. Now I mentioned SIMD because in the MIMD model, okay, we usually think of MIMD as having the processors not being synchronized with each other. Okay, so maybe like one processor can be faster than the other processors. So it can take 2 steps every time the other processor takes 1 step. Okay, but in the PRAM model, everything is synchronized. Okay, all of the processors take the same number of steps. All right. Now there's a few other things we need to talk about for this PRAM model, and the first one is memory conflicts. Okay, so the problem here is that we allow these processors to read from any location to read and write to any memory location. Okay, but what if in a time step we have several processors that want to read or write from the same memory location? Okay, maybe there could be some problems that arise because your memory, let's say, does not support having multiple concurrent accesses. Now, the way the PRAM model deals with that is that actually there are several submodels for the main PRAM model. Okay, there are 4 different submodels. So the first submodel is called the EREW model, which stands for exclusive read, exclusive write. Okay, and in this model, we simply do not allow the processors to read or write to the same memory location in the same time step. Okay, they can of course read to the same memory location in different time steps, but if they try to do this in the same time step, then the program is going to crash. Okay, so therefore, if you're writing a program for the EREW model, you have to make sure, you as the programmer, have to make sure that your algorithm is not going to read or write from the same location in the same time step. Okay. Now that is the most restrictive model of these 4 different models for PRAM. Okay, so the next model, which is less restrictive, is going to be called the CREW model. And this stands for concurrent read, exclusive write. And so here, what we allow is that in each time step, we allow several processors to read the same memory location. Okay, so unlike EREW, right, we do allow multiple processors to read from the same memory location in a time step. However, we do not allow them to write to the same memory location in the same time step. Okay, and again, if they do write to the same memory location in the same time step, then the program is going to crash. Okay, we can also talk about the ERCW model. Okay, so this is where you do not allow processes to read the same memory location in one time step, but you do allow them to write to the same memory location in a time step. Okay, but this is rather unusual, right? So usually we don't consider this ERCW model. And then the final model, so this is the most general model. Okay, so this is called CRCW, which stands for concurrent read, concurrent write. And so here we do allow multiple processors to read from the same location in one time step, and you allow multiple processors to write to the same location in a time step. Okay. However, if you do have multiple processors writing to the same location in a time step, right, then only one of those values can be written, right? Because it's a single memory location. So if you have multiple processes writing to it, you can't store all of those values. You can only store a single value. Okay, so then we have to somehow decide which value is going to get stored at this location if you have concurrent writes. And so here, there are a number of different possible choices. Okay, so in fact, the CRCW model, there are additional submodels of the CRCW model. Okay, so these submodels are different ways of deciding what happens when you have concurrent writes to the same location. Okay, so one possibility is that you simply let an arbitrary write succeed. Okay, so if you have 2 processes writing, then one of those values gets written. Okay, and it's an arbitrary one. Another possibility is that we have some sort of priority rule to determine which one is going to succeed. Okay, so for example, the processes might have some priority among themselves. Okay, so that means that if several processes write to the same location, then the highest priority processor, that value gets written. Okay, or maybe the priority is on not on the processors, but on the values that they're writing. Okay, so perhaps we have a way of implementing a priority where let's say the largest value being written gets written to a location. Okay, so that memory location itself can somehow do like a max operation when there are multiple concurrent writes. Okay, and we're gonna so we'll be using different ones of these CRCW models in some of our algorithms. Okay, and then when we use the CRCW model, we have to specify which type of arbitration we're going to use. Okay, whether we're letting arbitrary writes succeed or based on some priority or something. Okay, so this is how we deal with memory conflicts. So next, what do we hope to have when we design one of these PRAM algorithms? So the metrics that we're trying to optimize for PRAM, so there are 2 of them. One is called work, and the other is called depth. Okay, so So now the depth of a PRAM algorithm is just the number of steps this algorithm takes until it terminates. Okay, and it's a number of parallel steps. So remember that in each parallel step, all of the CPUs can do some work. Okay, so we're looking at how many parallel steps this algorithm takes before it terminates. And oftentimes we, because in the PRAM model, you're allowed to use many processors. Okay, then oftentimes we want to make sure that the depth of the program is very small. Okay, because if you're using many processors, you don't want all of those processors taking many steps. Okay, so oftentimes a goal that we have is to make the depth be polylogarithmic. So what that means is that if you have an input of size n, okay, then we want the algorithm to terminate in log of n steps, or maybe log of n to some power steps, okay, to some fixed power. So maybe log n squared number of steps, or log n cubed number of steps. Okay. Okay, and you also want the algorithm to but at the same time that you want it to terminate quickly, you also don't want to use too many processors. Okay, so we also want to use a polynomial number of processors. Okay, so maybe you want the algorithm to terminate in log number of steps using m processors, for example. Okay, or maybe log squared number of steps using n squared processors. Okay, those are sort of typical parameters that we try to achieve for PRAM algorithms. Okay, so that's the depth. And now the work of the PRAM algorithm is simply the number of processors that you use times the depth. Okay, so that's kind of like the maximum amount of computation that all of these processors can do in this amount of time that your algorithm runs for. Okay, and if you compare this to the work for a sequential program, right? Sequential program, the number of processors is 1, okay? And the depth is just the time complexity of the algorithm, okay? So therefore, the work of a sequential algorithm is equal to its time complexity, okay? And so if you remember from one of our very early lectures, so we talked about this thing called the work law. So the work law is simply saying that the amount of work done by a parallel algorithm has to be at least as large as the amount of work done by the best sequential algorithm for the same problem, right? So for example, if we're sorting, okay, then if the best sequential algorithm does n log n amount of work, then the amount of work that a parallel algorithm does has to be at least n log n. So the number of processors that we use times the depth has to be at least n log n. And if these two quantities are equal, right? If the parallel algorithm uses the same amount of does the same amount of work as the best sequential algorithm, then we say that the parallel algorithm is work efficient. Okay, so sometimes what you can do is you can trade off the work efficiency of an algorithm with its depth. Okay, so for example, you can sometimes make an algorithm which has very low depth, so it terminates very, very quickly. Okay, but the amount of work it does is maybe very large. Okay, or you can go the other direction where you can make the work be very small, right? Be as close as possible to the sequential algorithm. However, the depth might be quite large in that case. Okay, so there's this oftentimes there's this trade-off between the work and the depth. But in practice, we typically try to favor the work as opposed to the depth. Okay, so in practice, when you design a PRAM algorithm, you want to make sure that it's work efficient. Okay, even if that means the depth is a bit larger. Okay. And the reason you want to make this work efficient is that eventually, the reason that we're developing these PRAM algorithms is so that eventually we can try to run them on real hardware. Okay, now maybe you can't run the exact same PRAM algorithm on real hardware. Okay, and we'll talk about why that is on the next slide. But you want to run some version of this PRAM algorithm on real hardware. And so when that happens, right, on real hardware, you actually do not have a very large number of processors. Right? So if you're going to sort 1 million numbers, you're not going to use 1 million processors to do that. Okay, you have a limited number of processors, and so in that case, the running time of the algorithm in practice is usually determined by the amount of work that it does, not by the depth. Okay, and so that's why we want to minimize the work so that when you run this in practice, it actually performs well. Okay, now let's talk about how useful this PRAM algorithm is. Okay, so first of all, it's a theoretical model, right? Because it assumes that you have lots and lots of, you're allowed to have lots and lots of processors. Okay, like we said, if you're trying to sort 1 million numbers, then the PRAM model allows you to use 1 million processors. Okay, but of course in practice you would never do that, right? You might use like maybe 100 processors, or probably if you're sorting 1 million numbers, you would just use like one processor, or maybe yeah. Okay, so but the PRAM model allows you to use a lot of processors, which is not realistic. And the other very unrealistic part about the PRAM model is that it allows all the processors to access memory in every time step. Okay, so there's basically no cost to accessing memory in the PRAM model, right? Most of the cost is in the computation, right? Because the amount of time that we count for the PRAM algorithm, the depth of the algorithm is equal to the number of computation steps that each processor does. Okay. Now, this is very unrealistic to discount the time for communication, right? Because we saw that in almost all real models of computing, the main cost for computation is the communication cost. Okay, you can compute much faster than you can access data. So the main cost is actually in the communication, right? Whether it's the latency cost or the bandwidth. Okay, and so therefore the fact that the PRAM model ignores this communication makes it quite unrealistic. Okay, yeah. So those are the downsides to the PRAM model. Okay, is that it's not very realistic. However, it does have some advantages. Okay, and this is why we're studying the PRAM model, because it's a very simple and clean model, right? It's simply you have a lot of processors, and they can and they can read any memory they want. And so what we focus on in the PRAM model is just the computation. Okay, and in the PRAM model, you can try to design algorithms with as much parallelism as possible, because you're allowed to use as many processors as you want. Okay, so the PRAM algorithm really shows you how much parallelism there is in this problem that you're trying to solve. And so when you make the PRAM algorithm, the first thing you do is you try to maximize the parallelism. And then after you design this algorithm with like very large parallelism, but which is sort of unrealistic because it ignores these other factors, then the next step is to somehow convert this unrealistic PRAM algorithm into something that can run efficiently on realistic hardware. Okay, then the next step is you have to think about how to map your algorithm onto like a limited number of processors, and you have to consider the amount of communication cost between these processors. Okay, and it is possible to do this in practice. Okay, it is possible to make a theoretical PRAM algorithm and then somehow translate this so that it can run efficiently on actual hardware. So for example, many GPU algorithms, including some of the ones that we talked about, okay, they are adaptations of PRAM algorithms that take into account communication and other issues. Okay, but they started life as a PRAM algorithm. Okay, so this is why we're studying the PRAM algorithm. And so today we're going to look at some basic problems that you can solve in this model. Okay. So the first problem we're going to look at is this problem of parallel carry look-ahead addition. Okay, so the problem that we're trying to solve is that we're simply trying to add two numbers. Okay, so for example, here we're trying to add these numbers A and B. And the numbers are also expressed in binary. Okay, so it's a very simple problem. And yeah, and suppose what you're allowed to do is that you have a bunch of CPUs, and what these CPUs can do is they can only add single bits at a time. Okay, so you've got a CPU, and if you're just given 2 bits from A and B, then it can add those together. Okay, and it can also compute a carry from that operation. So for example, if you add the 1 and 1, right, you get a 0, and then you produce a carry to the next digit. Okay, and in practice, if you have these circuits called full adders, okay, then this is what they can do. Okay, they can take 2 bits and then add them together and then produce a carry. Okay, so now if you want to add together these 2 numbers, then if you do this sequentially, of course, it's going to take, if each number has n bits, right, then this is going to take order n time. However, if you have a like a computer processor, right, then we're usually dealing with like 32-bit or 64-bit numbers. And so if it takes you 64 time units to add together 2 of these numbers, then this is too slow. Okay, so we want to somehow do this in parallel. All right, now when you do this in parallel, part of this problem is easy, okay, because if you just take a digit from A and B, right, so you can have, if you're adding together n digits, you can have n of these full adders, okay, and each one of them can just take one of these digits of A and B and add those together, and you can do all that in parallel, okay. But the difficulty is that after you add A and B for one digit, right, for some digit, you could produce a carry, and then this carry needs to be included in the computation for the next digit, right? And then by including that, you could generate another carry, which needs to be included in the computation for the next digit. Okay, so for example, if you add together this 1 and 1, right? Well, then this generates a carry over here, right? Which is also going to generate a carry on the second bit. And so that is going to affect the result in the third bit. Okay, so the computation in the first bit affects the result in the third bit. And in general, any digit can have an effect on any other digit which comes later. Okay, so this makes it more difficult to do this problem in parallel. Okay, because now you can't just compute all of these individual digits like independently, right? Because the answer for each digit might depend on the answers for previous digits. Okay, so then, right, okay, so then what are we gonna do? So first of all, on the right over here, okay, so I just wrote a truth table for what we're supposed to compute, okay? So given the ith digit of A and the ith digit of B, and then suppose we also have a carry bit that is included in the ith bit, okay? So for example, this bit over here would be the carry bit for the second digit, okay? Then we're supposed to output this sum bit. Okay, so for example over here, right, this would be A1, right? Sorry, A2, right? Write this nicer. Okay, this is A2. This is B2, right? This is going to be C2 over here, right? This is S2, the sum for the second digit, right? And then we're also going to produce a carry. Okay, so this carry is this thing over here, and so we're going to produce this carry for the third bit. Okay, so this is a computation that we need to implement. All right, so how can we do this in parallel? Well, it turns out that there's a way to compute all of the carry. So if you do this in the normal sequential method, right? So where you go digit by digit, okay, then it's going to take you order n time to compute all of the carry bits. Okay. But it turns out that there's a faster way to do this, and you can actually compute all of the carry bits in parallel in only log n time. Okay, so n is the number of digits, and to do this, we're also going to use n processors. Okay, where each processor is a full adder. All right, now assuming that we can compute all of these carry bits in log n time. Okay, then after that, we can compute the answer also in an additional constant amount of time. Okay, because each answer is simply equal to the sum of the two digits in that the sum of those digits from A and B, right, plus the carry bit. Okay, yeah. So the key part is to compute these carry bits. All right. Now to do this, in order to simplify our notation, I'm going to so all of these computations are based on the AND and OR operations. Okay, with Boolean variables. But to simplify the notation, I'm going to denote AND by this this little multiplication sign, and then the OR I'm going to denote by the addition sign. Okay, so using this notation, we're going to define a few other variables. So the first variable is that for the ith bit, okay, we're going to define something. We're going to define this g sub I. This is going to be called the ith carry generate bit. Okay, and the reason it's called the ith carry generate is so this g of I is equal to a of I times b of I. Okay, and that means that if both ai and bi are 1, right, then gi is going to be 1. Okay, and the reason it's called the carry generate bit is if ai and bi are both 1, right, then the next digit, there's going to be a carry on ci plus 1, no matter what the current carry is. Okay, so for example, if the current carry is 0, right, then because we have ai and bi both equal to 1, they're going to generate a carry on the next bit. Okay, and if the current carry bit is 1, right, then when you combine that with ai and bi, we're also going to generate a carry on the next bit. Okay, so if ai and bi are both true, then we're going to generate a carry, right? And if one of them is false, then we don't necessarily generate a carry. We still could generate a carry. Okay, so next we're going to define another variable, this p sub I. Okay, so the p sub I is going to be the exclusive OR of ai and bi. Okay, so we're going to call p sub I the carry propagate bit. Okay, so basically, if pi equals 1, then we're going to have that the next carry bit is equal to the current carry bit. Okay. And the way that you can see this is, if pi equals 1, then either we have 1 0. So then if you look at ai and bi, okay, either they're 1 0 or they're 0 1. Okay, so that's the only way that you can make the pi be 1. Okay, and in the first case, if it's ai, if it's like 1 0, right, then the the next carry bit is equal to the current carry bit. Because if the current carry bit is 0, right, then we have, you have 1 0 0, and so there's no carry on the next bit. So this is going to be 0. Okay, and if on the other hand, the current bit we have a carry, right, then we're going to have 1 0 1, right. You add those together, and you are going to produce a carry on the next bit. Okay, and likewise, if if this is 0 and this is 1, it's going to be the same thing. Okay. All right, so then we define these two things, the PIs and the GIs. And now we claim that the next carry bit, okay, for digits I plus 1, is going to be equal to GI or CI and PI. Okay, so remember the plus means or, and the multiplication means and. Okay, and the way to understand this this equation over here is that so we're trying to figure out whether we have a carry bit on the next whether we have a carry on the next bit. Okay, and we're going to have a carry if either the current bit ai and bi, either if they generate a carry. Okay, so if gi is 1, then that means that ai and bi generate a carry. Okay, so they're going to force us to have a carry on the next bit. Okay. Or if ai and bi are going to propagate the carry from the current digit. Okay, so that means that if ai and bi are going to cause this pi to be 1, okay, so that they do propagate the bit. Okay, and furthermore, if the current ci is also equal to 1, okay, then we're going to get a carry on the next bit. Okay, and if we do not propagate the bit, we do not propagate the carry, right? Then regardless of what this carry is, this is not necessarily going to cause a carry on the next bit. Okay, so we have this equation over here, and if you're not satisfied with the explanation I gave, then you can just explicitly compute all of these variables, and then you can see that indeed the next carry bit is related to the previous bits in this way. Okay, so in any case, we have this relationship over here, and once you have this relationship, then now we can try to compute all of these carries in parallel. Okay, so here what we're going to do is we're going to express the next carry bit in terms of this little matrix multiplication here. Okay, and what this says is that if you want to compute the next carry bit, okay, so we're going to treat this as a vector. So the first coordinate is the next carry bit, and then the second one is going to be true over here. Okay, and the claim is that this is equal to the current carry bit and then true times this little matrix over here. Okay, so the f and the t denote false and true. Okay, and the way you check this is that if you multiply the first row by this vector here, right, then you get pi times ci, right, plus gi. Okay, gi times t is equal to gi, right? Gi and true is going to be equal to gi. Okay, so the top part here is going to be ci and pi or gi. Okay, and the bottom part is going to be false times ci, so that's going to be false. Okay, plus true times true. Okay, so it's basically false or true, and that's going to be true. Okay, so then we have this relationship. Okay, and then we know that by the previous page, we know that ci times pi plus gi is equal to the next carry bit. So this is saying, so therefore, what this says is that if you take the current carry bit and then true, and then you multiply it by this little matrix over here, you're going to get the next carry bit. And now you can actually do this multiple times. Okay, so we know that we have this relationship. Okay, but ci true is also equal to if you take the I minus first carry bit, right, and then you multiply by these p and g values from the I minus first bit. Okay, then you're going to get the ith carry. Okay. And so, and then this value over here, okay, the ci minus 1 true, you can again expand that, okay, into something in terms of ci minus 2 and then true, and then times another matrix over here. So then you can just do this entire expansion, and then in the end, you're going to see that the I plus first carry bit is going to be equal to the product of all of these little matrices, okay, times the initial carry bit. Okay, so now why is this useful? Well, the reason this is useful is because each of these values, okay, all of these pi and gi values, okay, they can be computed in parallel. Because if you go back to the to how we define these pi and gi values, right? So pi is just the and of the 8th bit of I and b. Okay, so we can compute all of these gi values in parallel. Right, we can take all these ands in parallel. And the pi is going to be the exclusive OR of ai and bi. And so again, we can compute all of the pi's also in parallel. Okay, so that means that once we have this equation, we can actually compute all of these values in parallel, and then we can store them somewhere. So we can form all of these matrices in parallel. Okay. And so then what we need to do is we just need to multiply all these matrices together. Okay, but this is actually a prefix product operation. Okay, because what we're doing is that we are given, we start out by computing all of these p and g values in parallel. Okay, so we have p1g1 all the way up to pngn. Okay, so now think of these as inputs to our algorithm. And now what we want to do is we just want to multiply together all of these matrices. Okay, so for the in order to generate the I plus first output, you want to take the first I matrices and multiply them together. Okay. Now this is simply a prefix product operation. Okay, so prefix product means that to generate the I plus first output, you take the first I inputs and multiply them. And that's exactly what we're doing over here. Okay, so now we have parallel algorithms to do these prefix products in parallel, right? And in fact, we can do that in log n time. We can produce the prefix products for n input values in log n time if we use m processors. Okay, so we talked about those algorithms earlier. And so that is what we're going to do over here, right? We're going to have m processors and we're going to compute all of these prefix values in parallel in log n time. Okay, and so this shows that we can compute all of these carry bits in log n time, and once we have those, then we can just we can combine the carry bits, and then we can produce all of these sum bits in log n time. Okay, and this is what we want to do, right? We just want to compute these sum values. Okay, so yeah, so that's the algorithm for parallel carry look ahead, and this algorithm is actually used in practice. Okay, this is either this algorithm or some variation of this algorithm is what is implemented in real CPUs. Okay, so next we're going to look at another problem, and this is about finding the max of a set of numbers, a set of inputs. Okay. Now we're going to look at two algorithms. So the first algorithm is going to be super fast. Okay, it's going to be, in fact, it's going to find the max of n numbers in constant time. Okay, but it's not going to be work efficient. And then later we're going to look at another algorithm, which is going to find the max of n numbers, and it's going to do this in log n time. Okay, so in particular, now we know of a simple way to find the max of n numbers in parallel, right? And we can do this in log n time using order n amount of work simply by using a balanced binary tree, right? So if you just make a tree, right, and then you associate processors to the nodes in this tree, then each of these processors is just going to take the max of its two inputs. Okay, and then if you do this, then eventually the top node in the tree is going to produce the overall max of all n inputs, right? But this is going to take us log n time, right? And it does order n work. So so instead, it turns out that there's a much faster algorithm which works in log n time. Okay, so exponentially faster than this tree algorithm. And it also does order n work. Okay. However, in order to run this algorithm, we need to use the CRCW model. Okay, so we need to have both concurrent reads and concurrent writes. Okay, and furthermore, we need the concurrent writes to have this min priority method of resolving conflicts, which means that when you have multiple values being written to the same location, then the minimum value wins. Okay, so we're trying to find the max, but we need this min priority CRCW model. Okay, so now let's first talk about this constant time algorithm to find the max. Okay, so the way this works is that suppose you're trying to find the max of p numbers, okay, x1 up to xp. Then what we're going to do is we're actually going to use p squared number of processors. Okay. And we also need to use the CRCW model. Okay, so with min priority. Okay, so so then what we're going to do is for each, so we have p numbers and then p squared processors. So then for every pair of numbers, okay, so let's say for xi and xj, okay, we're going to assign one processor to that pair of numbers. So then we have p squared pairs of numbers, and so that's why we have p squared processors. And then for each of these processors, what it's going to do is it'll compute this value b of ij, which is equal to 1 if xi is at least equal to xj. Okay, and otherwise it's going to be 0. Okay, so this processor simply compares xi and xj. Okay, if xi is at least as big as xj, then it's going to have set a bit to be it's going to have this value 1. And then next, what we're going to do, so we can do all of these computations in parallel, of course. Okay. And then next, what we're going to do is we're going to compute this value m sub I here. Okay, and m sub I is equal to all of these b values. Okay, bi1, bi2, and so on, all the way up to BIP. It's equal to the AND of all of these b values. And so that means that yeah, okay, it's equal to the AND of all of these b values. Let's see. This requires that one. Yeah. Okay. So so now notice that m sub I. Okay. It's only going to be 1 if all of these b values are equal to 1. Okay. But if all of these b values are equal to 1, right, then each of these values indicates. So for example, this value. Okay. This is going to be 1 when the when xi is bigger than is at least equal to x1. Okay. So the fact that bi1 is 1 indicates that xi is bigger than x1. Okay. And if you want this to be also 1, right, then this means that xi has to be bigger than x2. Okay, and so on. And if we want mi to be 1, right, then we need all of these bits to be 1. Okay, and that would mean that xi is bigger than all of the other values. Okay, it's bigger than all other xj. And that means that xi is the max value. Okay, so therefore we have that mi is equal to 1 if and only if xi is actually the maximum value. Okay, now in order to compute this mi, okay, here's where we actually use this CRCW property with min priority. Because what we want is that, so here, you know, we could have some of these bits being equal to 0, right? If xi is not the maximum value, then some of these bits are going to be equal to 0. And what we need is that, so we're going to have P processors writing to the same memory location, the same mi. And what we need is that when you have different values being written, when some values are 1 and some values are 0, then you need that the 0 actually gets written. Okay, so what we want is if any of these b's is 0, then we're going to set mi to be 0 here. And to do that, we need, first of all, we need to allow concurrent writes to this mi, okay, because all of these P processors are writing to this mi. And furthermore, we need that if many different values are being written, then the minimum value is the one that gets written. Okay, so in our case, the minimum value will be 0. Okay. All right, so yeah, so then we have this algorithm for finding the maximum of P numbers in constant time. Okay, because it just does 2 steps, right? It first of all computes these b values, and then it writes to this m location. So it works in constant time. However, it does p squared amount of work, right? Because we have p squared processors, and they each take 2 time steps. So that's p squared amount, order p squared amount of work. Okay, now we're gonna take this constant time algorithm, and we're gonna convert it to another algorithm. And so this algorithm is going to be much faster than the balanced tree method, and it's going to be work efficient. Okay, so the way we do that is we're not going to use a binary tree anymore. Okay, we're going to use a what's called a doubly logarithmic tree. So the way this works is that we're first of all going to create a tree with all of these input values, these input x values as the leaves. Okay, and then for each internal node in the tree, for each internal node u, right, then if you look at how many leaves are in the subtree rooted at u, okay, then we're going to make the degree of u be equal to this quantity here. Okay, the ceiling of the square root of the number of leaves in the subtree rooted at u. So for example, if you take this node, if this is u over here, okay, then there are 16 nodes in the subtree rooted at u. So therefore, we're going to make the degree of u be equal to the square root of 16, which is 4. Okay. Now over here, right? If you look at this u, then the number of nodes in its subtree is 4, and so we're going to make the degree of that be the square root of 4, which is 2. All right, so now this is the main property about the tree. So this is called a doubly logarithmic tree because basically its height is going to be log n. Okay, if you have n leaves, the height is going to be log n. Okay, and the way that you can yeah. So then because its height is log n, then for convenience we're going to assume that n is actually going to be 2 to the 2 to the k. Okay, so this way, if you take log of n, you get an even, you get a number. Okay, you get a integer number. Okay, so now let's look at the degrees of different nodes. Okay, so we said that the degree of a node is equal to the square root of the number of leaves in its subtree. So therefore, the degree of this top node over here, right, because it has n nodes in its subtree, right, because everybody is in the subtree, then the degree of the top node is going to be square root of n. All right, and then next, so the degree here is square root of n, and in fact, all of these subtrees after the root, they all have the same size. They all have size square root of n. Okay, because we have square root n of these different subtrees, right? We have 4 of these subtrees, and so each one of them is going to have size square root of n. Okay, so square root of n equals 2 to the 2 to the k minus 1. Okay, so therefore the degree of each of these nodes, right, because it's got 2 to the 2 to the k minus 1 nodes in its subtree, then the degree is going to be the square root of this, right? And the square root of this is actually just equal to, here you can make it k minus 2. Okay, yeah, so each of these children has degree 2 to the 2 to the k minus 2. Okay, and it's the same idea as you keep going down the tree. Okay, so each time you go down the tree, then the number of nodes, the number of children of that node is gonna be square root of the the size of the entire subtree. Okay, and the degree is also gonna get the degree of one of its children is also gonna get square rooted. So therefore, at the ith level of the subtree, then each node is gonna have this degree. Okay, so and then using this, we can also figure out the total number of nodes at each level. Okay, so for example, this level has 4 nodes. Okay, and this level has 8 nodes. Okay, and so the way that you figure out the total number of nodes at each layer is that, well, in the first layer you have so in the first layer we branch 2 to the 2 to the k minus 1 ways. Okay, we have degree 2 to the 2 to the k minus 1. Okay, and then in the next layer, we have each node has degree 2 to the 2 to the k minus 2. Okay, and so on. So then when you get to the ith layer, okay, the number of nodes at that ith layer is going to be 2 to the 2 to the k minus 1, right, times 2 to the 2 to the k minus 2, right? Because as you go from the first layer to the second layer, then you generate this number of nodes. Okay, times when you go to the third layer, you have 2 to the 2 to the k minus 3. And then so on, okay, until you get to this layer, which has degree 2 to the 2 to the k minus I. Okay, so this is the number of nodes at the ith layer. And then if you want to evaluate this this product over here, well then the product of all of these is you can just take all of these exponents and you can add them together. Okay, so then this is equal to 2 to the 2 to the k minus 1 plus 2 to the k minus 2 plus, and so on, right, plus 2 to the k minus I. Okay, and so this here is a geometric series, and if you add that up, then this is what you're going to get. Okay, so that's how you count the total number of nodes at that layer. All right, so then, so this is how we define this doubly logarithmic tree. And now we're going to use this tree to compute the max in log n time. Okay, so the way we do this is that suppose each node computes the max of all of its children. Okay, yeah, and then if you do that, then as you propagate these values from the leaves to the root, right, then eventually the root is going to end up with the max of all of the values. Okay, so right. And now when you compute the max of your children, okay, if you have p children, then we saw this algorithm where you can compute the max of these p children nodes in constant time, but in p squared amount of work. Okay, and right, and so now the total time for this algorithm is just because each of these computations at each layer takes constant time, and we just have to go all the way up the tree, and the tree has height log n. Okay, so therefore the time to run this algorithm is going to be ordered log n. Okay. And the amount of work that we do at each level, okay, is going to be, well, we have, so we have, the degree of each node is going to be 2 to the 2 to the k minus I minus 1. Okay, so this is what we said, previously, right? The degree is going to be this, right? And the number of nodes is going to be this. Okay, so therefore the amount of work that each node at that at the ith layer does, okay, is, well, it has this degree. Okay, so it has this number of children. So p equals this value over here. Okay, p equals this value, right? And so the amount of work that it does to find the max of those children is going to be p squared. So it's going to be this value squared. Okay, so basically that means that this 1 is going to get removed. Okay, and then we multiply this by how many nodes there are in that level. Okay, and we said that there are that many nodes in that level, in the ith level. Okay, so therefore if you multiply these two together, then this part is just going to cancel out. And so we simply get that the amount of work at this level is equal to 2 to the 2 to the k. Okay, and this is equal to order n. So therefore, the amount of work at each level is order n. And then the total work for the entire algorithm is going to be just n work per level times the number of levels. Okay? Right, so this is not quite a work-efficient algorithm yet, right? Because to be work-efficient, then you know, the work that you need to do to find the max of n numbers is simply n. Okay, and then here we're doing n times log n amount of work. So we're not work efficient yet. Okay, so then in order to make this work efficient, what we can do is, yeah, so then we're going to use a technique called accelerated cascading. And basically this technique is to start with a work efficient algorithm, okay, and then keep using that until the problem is sufficiently small, okay, and then you're going to switch to once the problem size gets to be very small, then you're going to switch to a very fast algorithm, but which is not necessarily work efficient. Okay, so you start with a somewhat slower algorithm, but which is work efficient. You keep applying this algorithm, and it's going to subdivide the problem until the problem size gets to be small. And then you're going to finish up with this very fast algorithm, but which is not work efficient. Okay, so yeah, all right. So the way we do this actually is that we're going to take these n values, okay, and you're going to divide them into a bunch of blocks. You're going to divide them into n divided by log n blocks, and then each block is going to have log n values in it. Okay, and now we're also going to use n divided by log n number of processors. Okay, so we have the same number of blocks as processors. And so each processor gets assigned one block, right? And it's just going to find the max value in the block it's assigned. Okay, so it's assigned a block of log n numbers, and if it wants to find the max, it'll just go through all these numbers sequentially, right? And then find the max. Okay, and so each of these processors is going to take log n time to go through all its numbers. And the total amount of work that this does is that, well, we have n divided by log n processors, and each one of them takes log n time. So the product of these is the amount of work. Okay, so the product is going to be order n work. All right, so yeah, so the first step is to find the break these into that many blocks and then get this number of maxes, right? Because each block is going to end up with one max of that, one maximum value of that block. All right, and then once we get this number of values, then now we're going to apply this very fast, this doubly logarithmic tree algorithm to find the max of all of these values, okay, of all of these values. Okay, so let's say that m prime here is equal to m prime here is equal to this n divided by log n. Okay, so we're going to use a doubly logarithmic tree on the m prime values that are obtained from the blocks, and the running time for this algorithm is just going to be log of m prime, right? And so this is going to come out to basically order of log n. Okay, because n prime and n are very close to each other. Okay, so this is going to come out to order log n. And the amount of work that this does, okay, is going to be equal to m prime times log m prime. Okay, because we saw from the previous page that if you just use this this doubly logarithmic tree, then the amount of work that you do is equal to the number of nodes in the tree times log of that number. Okay, and in our case, we have just m prime values that we're applying this tree on. Okay, so then so then the total amount of work is going to be m prime times double log m prime, right? And double log m prime is basically going to be this thing here is basically going to be is going to be equal to order of log n. Okay, and then this m prime here is equal to n divided by log n. So therefore, if you multiply by this double log n over here, then we get that the total amount of work that the second phase does is order n. Okay, so we have this two-phase algorithm. Okay, the first phase is you break the values into blocks and then you add them sequentially. So that's going to take double log time and linear work. Okay, and the next phase is that we're going to apply this doubly logarithmic tree on all of the values from the first phase, and that's also going to take double log time, and it's now going to do only linear work. Okay, so then altogether we do linear work and double log time. Okay, so we have a very fast and work efficient algorithm to find the max of many numbers. Okay, but we needed the CRCW model with the min priority to do this. Okay, so we're going to talk about another problem now. So this problem is called list ranking. Okay. So this is a very useful problem, and it's used in many other. It's used as a subroutine in many other algorithms that we need to look at. Okay. So the basic problem is that suppose you're given a linked list like this over here. Okay. Then so the linked list is going to have let's say a bunch of these nodes in it. Okay. So each of these values is going to be different. Okay. So here we have 6 nodes and 6 different values. And what you want is for each node to find the distance from the head of the list. Okay, so for example, the head of the list is this 2 value over here. Okay, so this has a distance of 0 from the head. Right? And then the next node is going to be 0 over here, so it's got a distance of 1. Okay, and this guy has a distance of 2, 3, 4, 5. Okay, so so our input is simply going to be this linked list, right? And the output is for each node to compute its distance from the head of the linked list. Okay, so how is this linked list represented? Okay, well, the way it's represented is just that for each node knows the next node in the list. So for example, this 2 here, okay, it doesn't have a next node, so therefore for node 2 over here, we're going to mark the next node from 2 to be this bottom. Okay, this indicates that 2 is at the head of the list. Okay, and then after 2, we have this node 0 over here. Okay, so 0 is going to say that the next node after 0 is 2. Okay, and then before the 0, we have a 3. So the 3 is going to say that the next node after 3 is going to be the 0. Okay, and so on. So this is our input that we're given. Okay, this is how the input is represented. And then again, the output is for each node to compute its distance from the head of the linked list. Okay, so the way we're going to do this is, well, initially we can find the head of the list very easily. Okay, because the head of the list is going to have the next pointer be bottom. Okay, so every node can just check whether its next pointer is bottom, and if it is, right, then you found the head of the list. And the head of the list has a distance of 0. Okay, and then the other nodes in the list, what they can do is that, well, they can find their distance from the next node, right? Because, for example, this 3 node here, right, it knows that the distance to the next node is simply a 1 over here. Okay. Likewise, this node 0 over here, right? It knows that the distance to the next node is a 1. Okay. So yeah, so all of these nodes initially know that their distance to the next node is going to be 1. Okay. Now, the next thing that we can do is that because 3 knows its distance 1 from 0, and then 0 knows its distance 1 from 2, right? Then if we add these together, then 3 can know its distance. It's going to be distance 2 from the node 2. Okay, and in fact, this is the correct distance of 3 from the head of the list. Okay, and then after that, so once 3 knows that it's distance 2 from the head of the list, right? Then because 5 knows its distance 1 from 3, then 5 knows that it's distance 3 from the head of the list. Okay. Yeah, so in this way, we can actually sequentially compute the distance of all of these nodes in order n time. Okay, but then the question is, how do you do this in parallel? And the way we do it is we're going to apply this technique called pointer jumping. Okay, and we're going to repeatedly apply this technique. So the way, so pointer jumping, what it does is that, so these nodes, in this algorithm, they have pointers to some other nodes. Okay, so for example, initially every node just points to its next node, but we could also have nodes point to other nodes. So for example, you could have a 5, you could have the 5 node point to the 0. Okay, and what pointer jumping does is if node I is pointing to j, and if j is pointing to k, then we're going to just combine these two pointers, and we're going to have I point to k. Okay, so this is pointer jumping. And once you have this pointer jumping, then we can just repeatedly apply this pointer jumping in order to compute the distances. Okay, so yeah, so the algorithm for doing this is going to be over here. Okay. Yeah, so every node is going to keep executing until its next pointer is equal to null, okay, or this bottom symbol. Okay. Yeah, and then what they do is in each time step, we're going to have all of the processes operate in parallel. Okay, and the process is going to say that if its next pointer is not equal to this bottom, okay, not equal to null, okay, then its distance is going to be equal to its distance to the next node, right? Sorry, its current distance plus the distance of its next node. Okay, and also the next node, right? And here's where you apply pointer jumping. The next pointer is going to be equal to the next pointer of the next node. All right, now to make this a bit more clear, let's just do an example here. So initially, we're going to have these nodes in the linked list, okay? And there's only a single node. So this node at the end, right, its next pointer is going to be bottom here. So it knows that it can terminate, okay? And then in each of these time steps, what we're going to do is, in parallel, every node, so these values over here, okay, initially all these values are 1, okay? These are the d values. So the d values are estimates of the distance of a node from the start of the list. Okay, and initially all of these estimates are 1. And what we're going to do is we're going to set the d value be equal to the current d value plus the d value of the next node. Okay, we're going to do all of those in parallel. Okay, so for example, this node over here, right, it's going to set its d value to be equal to its current d value, which is 1, plus the d value of its next node. Okay, so that so it's going to keep it as 1. Okay, and then this node, right, it's going to set its d value to be 1 plus the d value of the next node, which is also 1. So it's going to set that to be 2. Okay, and the basic idea here is that, if this node actually has an accurate distance to the front of the list, okay, and if furthermore, if this distance between this node and the next node, if that distance is also accurate, then if you simply add together these two distances, then you get the correct distance of this node to the end of the list. Okay, so that's the basic idea. And we do all of this in parallel. So therefore, in the first time step, we're going to get these values for the distances. Okay, and then we do this again. And you're going to see that, so for example, this node, right? This node's next pointer is going to become zero, is going to become null after it does pointer jumping once, okay? Because it's going to do this line, so it's going to set its next pointer to be the next pointer of the next node. Well, the next node is this guy whose next pointer is null, so therefore this guy's next pointer is also going to be null, okay? On the other hand, this guy's next pointer, right? He's going to point at the next node from his next node. So therefore, he's going to point over here, right? He's going to point to the final node, okay? And this node over here, right? His next pointer is going to point to the next node after the next node. So therefore, he's going to point over here, okay? So then we have all of these new next pointers and these new distances. All right, now you're going to apply this parallel step again. And what that's going to do is, well, this guy, his next pointer is now null, so he's not going to do anything, okay? Because he's only going to do something if his next pointer is not null, okay? These other guys, so for example, this guy, okay? He's going to set his new, he's going to set his distance to be equal to this distance plus his current distance, right? So that's going to become 2. And his next pointer is going to become the next pointer of his next node, which is going to be this null here. Okay, so he's going to set his thing to be null. Okay. Now this node, right, this node, okay, he's going to set his distance to be equal to his distance plus the next node's distance. So that's going to be 3 over here, right? And then his pointer is also going to be the next pointer from the next node, which is going to be this null here. So he's also going to set this to null. Okay. And then let's do one more node. So if you pick this node over here, his distance is going to be 2 plus 2, which is 4. And his next pointer is going to be, he's going to follow the next pointer from the next node. And that's going to point to this 0 node over here. Okay, so he's going to point to the 0 node. Okay, and this guy is going to point to the 1 node. Okay, and then if you do this for one more phase, then what you're going to end up with is that the distances are going to be like this, okay? And then everybody's next pointer is going to be null. And at that point, the algorithm is going to stop. Okay, so yeah, so that's the algorithm. And basically, to see that the algorithm works correctly, so the property that we have is that what you can see is that if you run this for I steps, okay, then the then for each node k, its distance value is going to be the minimum of m, which is the total number of nodes, or 2 to the I. M is not the total number of nodes. M is the distance of node k from the end of the list. Okay, so m is actually the value that k is trying to compute. Okay, so yeah, so the distance is going to be the minimum of the correct distance and 2 to the I. Okay, so basically, when I is small, right, then the minimum is just going to be this 2 to the I value here. But eventually, when I gets to be at least log of m, right, then this m value here is going to be the smaller one, and then that says that this node k is going to have the correct value after log m steps. Okay, so that's one property, and the next property that we need is that these are invariants that the algorithm maintains. Okay, so the first invariant is that after I steps, right, the distance of each node is going to be the minimum of the correct distance and 2 to the I. And the other invariant is that the next pointer of this node is going to point at a node which is the minimum of m or 2 to the I distance away. Okay, so looking at this example here, right? So after you run for one step, okay, then basically every node's distance is going to be the minimum of its correct distance and 2 to the 1, okay, or 2. Okay, so you see that, for example, this node has the correct distance, okay, because his m is going to be equal to 0, so he actually has the correct distance after one step. Okay, this guy has the correct distance after one step, right? And then this guy has the correct distance after one step. Okay, but this guy, he does not have the correct distance. Okay, his distance is currently equal to 2 to the first power. Okay, so all of these other guys, so only the first 2 to the I nodes have the correct distances. Okay, all of the other remaining nodes do not have the correct distance yet. Okay, and also all of the nodes are going to point to a node which is the minimum of m and 2 to the I distance away. Okay, so for example, this node is going to point to a node which is distance 2 away. Okay, this node is also going to point to a node that's distance 2 away. And then on the next phase, right, these nodes are now going to point to nodes which are distance 4 away. Okay, well, the minimum of m and 4. Okay, they're going to point to a node that's distance that value away. Okay, and also their d values are going to be equal to the, once you look at this third phase over here, the d values are going to be equal to the minimum of the correct value, right, and 2 squared, okay, which is 4. Okay, so that means that the first 4 nodes, right, they have the correct values. Okay, and anybody beyond the first 4 nodes, their d value is still equal to 4. Okay, and then if you run this on another iteration, right, then you're going to have that the first 8 nodes are going to have the correct d values. Okay, and their pointers are going to point at this distance away. Okay, so then you can show that. So you can see that we're going to maintain these invariants, and since the final distances are all going to be less than are all going to be at most n, right? N is the number of nodes. Okay, then this algorithm is going to terminate after log n number of steps. Okay, and the total amount of work that we do is well, we have m processors. Right, for each of these nodes, we're going to assign a processor, and so since you run for log n number of steps, the total work is going to be n log n. Okay, and this is not work efficient because if you do sequential list ranking, right? Sequential list ranking, you just everybody just follows its next pointer until it gets to the end, right? That would take order n work. Okay, so we're doing n log n work right now. Okay, so we're going to see a way to make this work efficient a bit later. Okay, but first of all, I want to mention that this list ranking algorithm, okay, even though it might look a bit artificial, it's actually very useful. Okay, so just like the prefix sum operation was very useful, this list ranking algorithm is also in the PRAM setting where you have these pointer. So you have many problems which are based on pointers, right? For example, graph problems, right? You have these edges, and the edges are represented by pointers. Okay? So in these types of problems, list ranking is very useful. So we're going to see several applications of list ranking. For example, there's this thing called the Euler-Tor technique. Okay, and that technique is going to be based on list ranking. And then and then we also are going to use list ranking for things like connected components, and then evaluating expression trees, and many other problems. Okay, and then this Euler-Tor technique, this also forms a subroutine for many other problems. Okay, so list ranking is a subroutine for Euler-Tors, which in turn is a subroutine for many algorithms which are run on trees, many parallel PRAM algorithms on trees. Okay, so we're going to see those algorithms in later lectures. Okay, but the first thing to do, but before we do that, let's first look at a variation of the list ranking problem. So now let's try to compute a prefix sum on a linked list. Okay, so previously we saw how to do prefix sum on an array. Okay, so if your input is given as an array, then we had a fast parallel algorithm for computing the prefix sum. Okay. But now suppose your input is given as a linked list. Okay, so just like for the list ranking problem, suppose you this was your input. Okay, and now let's say that you have a bunch of values. Okay, so suppose these values here are no longer the IDs, but they're the actual input values. Okay, then if you want to compute a prefix sum on this, right, then this guy should be outputting 2. Right, this guy should be outputting 0 plus 2, which is again 2. Right, this guy outputs 3 plus 2, which is it's 5. Right, and this guy outputs 10, 14, and then 15. Okay, so this is what we want to do. This is how we can do, this is the problem that we're trying to solve, which is prefix sum on a linked list. Okay, so initially we're going to assume that each node I has an input value x of I. And then the output value is going to be stored in this variable d of I here. Okay, and so to do this, it's basically going to use the same algorithm as for list ranking. Okay, the only difference is that in list ranking, remember that we updated the d of I values. Okay, so d of I was set equal to d of I plus d of the next value. Okay, whereas for prefix sum, we're actually going to update the d of the next value. Okay, instead of d of I. Okay, and basically the reason for that is that if this is our initial linked list, okay, then what we want is these later nodes to have higher values, right? Because these later nodes, their output value needs to be the sum of all of these nodes preceding them. Okay, so then what this does is it sets the next node's value to be this node's value plus the next node's current value. Okay, so it sort of propagates the earlier values forward, okay, towards the end of the list. And that's what you want for prefix sum. Okay, and then otherwise, this algorithm is doing the same thing as the list ranking algorithm. Okay, so let's just go through this example just to see what's happening here. Okay, now in this example, these values in brackets, what this represents is the sum from the first value up to some other value. Okay, so or sorry, not the first value, but if you have a a value ij here, okay, it represents the sum from the ith value to the jth value. So initially, each node is only going to start with its own initial input. Okay, so initially this node only has a sum from the first value to the first value. So that's simply the first value. Right? And then this guy has a sum from the second value to the second value. So that's just the second value. Okay, so each of these nodes initially starts with just its own input value. All right, and then next, if you apply one round of this value propagation and the pointer jumping, then what's going to happen is first of all, each of these pointers is going to double in distance. Okay, so previously they were pointing at a node which is distance 1 away, and now they're going to point at a node which is distance 2 away. Okay. And furthermore, so in the first iteration, for let's say I equals 1, okay, then you have 2 to the I power equals 2. And so what's going to happen is that the first two nodes are going to have the correct prefix sum values. Okay, and the remaining nodes are going to have the sum of the previous two values, okay, of the previous 2 to the I, which in this case is equal to 2, okay, of the previous two values. Okay. So, so for example, this node over here, okay, when you do the top line when you do this line over here, right? Sorry, that's when you do this line, okay, this is saying that this processor over here is going to take his value, right? This processor is going to operate on the next node, okay? So he's going to set this guy's value to be equal to this guy's current value plus his own value. So then that's going to make this guy end up with the sum of the first value and the second value. Okay, so that's what this 1, 2 indicates, right? He's got the sum from the first value to the second value. Okay. Likewise, the processor over here is going to set the value over here, right? So he's going to set this value to be equal to the current value over here, which is just the third value, plus his own value, which is the second value. Okay, so then this guy's going to end up with the sum of the first two values, of value 2 and value 3. Okay, and likewise, this guy's going to end up with the sum of third and fourth value, and so on. And so you see that here you have the first two values, the first two nodes have the correct prefix sum values already, right? And then the other nodes, the remaining nodes, have only part of the prefix sum. Okay, so they only have 2 values from the prefix sum, right? This guy's got two out of 3 values from the prefix sum. This guy's got 2 out of 4 values from the prefix sum, and so on. Okay. Now, if you run another iteration, then that's going to it's going to double the number of nodes which have the correct values. Okay. It's also going to double the length of all of these pointers. Okay, the distance of all of these pointers. Okay. And further, and then finally, for the nodes which do not have the correct value yet, right? Well, they're going to have part of the prefix sum. Okay, and they're going to have the sum of the previous 4 values in the value that they're supposed to output. Okay, so in other words, for example, for let's say for this guy. Okay, now so we have a processor assigned to this node, and this processor is going to update this value over here, and he's going to set it to this current value over here plus his own value. Well, his own value is the sum of the first 2 values, and then this current value is the sum of the 3rd and 4th values. So when you add them together, you're going to get the sum of the first 4 values. Okay, so then this guy is going to end up with the correct prefix sum. Okay. On the other hand, this guy over here, right, his value is going to become the sum of this 2nd and 3rd value plus the 4th and 5th. So he's going to end up with the sum of the 2nd to the 5th value. So this is not the correct value yet, but it's 4 out of the 5 values that he's trying to add up. Okay, and likewise, this guy is going to have the previous 4 values. Okay, he's going to have the sum of the previous 4 values, but he's still missing the first 2 values from here. Okay, so then you run this once more, and now if you run this for another iteration, then this guy, he's only missing the first value. Okay, so then he's going to get the first value, and he's going to end up with the correct prefix sum over here. And this guy, he's missing the first 2 values, but he's going to get those 2 values, and so he's also going to end up with the correct value. Okay, so so that is the algorithm over here, and the invariant is that it's what we have over here, that after I steps, the first 2 to the I nodes have the correct prefix sum values, right? And the other nodes have the sum of the preceding 2 to the I values. Okay, so this means that once this value over here gets to be larger than n, gets to be at least n, then the algorithm has computed the correct output. Okay, and so therefore this only takes log n time, right? Before this value here is at least n, and then the amount of work that this does is again, we have n processors in each round, and so the total amount of work is going to be n times log n. Okay, so this is not a work-efficient algorithm yet, because the sequential running time for prefix sum is order n. Okay, so next, let's see how we can make the list ranking algorithm work-efficient. Okay, and then once we know this, we can also use the same idea and make the prefix sum be work-efficient. Okay, so to make it to make list ranking work efficient, what we're going to do is we're going to shrink this list until only n divided by log n nodes are left. Okay, so initially we start with n nodes, right? And then I'm going to tell you how we're going to shrink this list, and you're going to shrink it until only n log n nodes, n divided by log n nodes are left. And then at that point, you're going to do pointer jumping. Okay, and then after you do the pointer jumping, then here we shrunk the list, so we took out a bunch of nodes. Okay, well, we still need to have the correct output for the nodes that we took out. Okay, so therefore we're going to restore the nodes that we took out. Okay, and after you restore them, you're going to figure out their ranks. All right, so before I show you how we actually do this, let's just look at the work complexity if we manage to do all of these steps. Okay, so the total amount of work is going to be that. Now, suppose you can actually shrink the list, and you can restore the nodes that you took out. Suppose you can do both of these in order n time. Okay, order n amount of work. Okay, order n work. Then, if you look at the second step, okay, so this is where you would apply pointer jumping on this number of nodes. Okay, well, the amount of work that does is going to be however many nodes you have. Okay, if you have, let's say, n prime nodes, okay, then the amount of work is going to be n prime times log of n prime. So in our case, m prime here is going to be equal to n divided by log n. Okay, so therefore the amount of work for the second step is going to be this m prime times log of m prime, and this is going to come out to order n. Okay, so that means that the second step is going to take order n work. And so if we can also implement the first and third steps in order n work, then altogether we're going to take we're going to do order n work. Okay, and then we would have a work efficient algorithm. Okay, so then we have to figure out how to do the shrinking step and the restoration steps. Okay, so to do the shrinking step, okay, so we're trying to take n nodes and we're trying to remove some of them, okay, to make the list smaller. And to do this, we're going to keep removing an independent set of nodes. Okay, so what is an independent set of nodes? So what this means is, so a set of nodes I is going to be independent if basically we don't have consecutive nodes, both being in this independent set. Okay, so this means that if a node if a node little I is in this independent set, right, then the previous node cannot also be in the set. Okay, and also the next node from I cannot be in the set. So this way, all of these independent nodes are not pointing at each other. Okay, they're sort of they're not touching each other. Okay, so now suppose we have a set of n nodes. In the next lecture, we're going to see how we can find a constant fraction of these nodes. We can find an independent set which contains a constant fraction of these nodes. Okay, so if we have n nodes, we can find at least omega n number of independent nodes among these n nodes. Okay, so maybe like you start with 100 nodes, you can find, let's say, 33 nodes which are independent. Okay, so that's going to be a constant fraction of the current set of nodes. Okay, so we can find the set of independent, so we can find this independent set. The size is going to be at least a constant fraction of n, and the amount of time is going to be log n, and the amount of work is going to be linear. Okay, so we'll see how to do that next time. And then once you have this independent set, then you're going to take out this independent set of nodes. And when you take out these nodes, you're also going to set so for each node that we're taking out, okay, we're going to set the distance value. So remember that we're trying to compute these distance values for each node, right? The distance to the end of the list. We're going to set the distance value of the previous node to be equal to its current distance value plus the distance value of this I node from the independent set. Okay. So as an example of this, so suppose you start with this list over here. Okay. Now we're going to look at these values in the square brackets. Okay. Let's ignore these values in the parentheses. Okay. So these values in the parentheses are actually used to compute the independent set, and we're going to see how to do that next lecture. Okay. But we're going to focus on the values in the square brackets, right? These 1 values initially. Okay. And so these values are the initial estimates of the nodes of their distance from the end. So for example, this final node, right, it knows that it's at the end, so its estimate is 0. Okay, this node has an estimate of 1, and all of these other nodes start with estimates of 1. Okay, so now we're going to take out an independent set of nodes. Okay, so we're going to take out these nodes marked by the x's, right? And these are independent because you see that none of them are pointing at each other. Right, like for example, this node is not directly pointing to this node. Okay, now if we add this node to the independent set, then you cannot add this node also to the independent set. Okay, because they're pointing at each other. But we're gonna take this set of independent nodes, and for each one of them, whenever you take an independent node, right, node, you're gonna set the previous node. You're going to set that guy's distance to be equal to his current distance plus your own distance. Okay, so for example, when we took out this guy as an independent node, his previous node was the 7 over here. Okay, so then he set this guy's distance to be equal to the current distance, which is 1, plus his own distance. Okay, so this becomes a 2. Okay, likewise, this became a 2, okay, because this node 3 over here, right, he set this distance to be 1 plus 1, and so that's going to be 2. Okay, so we did this once, so you took out, you managed to take out a constant fraction of the nodes. Okay, but remember that you want to keep doing this until we remove n, until we're down to like n divided by log n number of nodes. So therefore, we have to do this again. Okay, we're going to remove another independent set of nodes. So starting from this, we're going to remove another independent set. And so let's say that you remove this 8 node over here and this 1 node over here. Okay, so those 2 nodes are independent. And when you remove them, then, for example, when you remove this node, okay, it's going to take its previous node, which is 6, and it's going to take the current distance and add it to its own distance. Okay, and it's going to set that to be a 4 now. Okay, and when you take out this node, right, it's going to take its previous node, which has a distance of 2, and add its current distance, which is 3. Okay. All right, and then we're going to do this. Let's say you do this one more time. Okay, if you do this one more time, we don't need to do this again. Okay, so now that we've done this for, let's say, 2 iterations, now suppose we're left with n log n divided by log n nodes. Okay, then we can just directly apply the pointer jumping technique at this point. And when you apply the pointer jumping, then you're going to compute that this node, he's going to get a distance of his own distance plus the next node's distance, which is 7. Okay, so then this node is going to end up with a value of 7 over here. Okay, so now we've reduced the set of nodes down to a small set of size n divided by log n. Okay, we've done the pointer jumping so that we computed all of the ranks on the nodes that we're left with. Okay, and now notice that for all of the nodes that we're left with, they actually have the correct distances. Okay, so for example, this node actually is distance 3 away from the end. Okay, and this node is distance 7 away from the end. Right? And the reason they have the correct distance is that each time we took out one of these independent nodes, right, we took its distance and added it to the previous node's distance. So that way we preserve the distance to the end, right? In other words, if you follow all of the points, so at any point in this process, after you've removed a set of independent nodes, if you follow all these pointers and then you add up all of these distances along the way, then you get the correct distance to the end. Okay, so for example, this guy, right? He is, so his correct distance is 1, 2, 3, 4, 5, right? And if you add up these distances along all of the pointers till you get to the end, right, then you also get 5. Okay, so as you remove nodes, we maintain this property that if you follow all of the pointers which are still remaining, then you can compute the correct distance. And so this is why after we took out all the independent sets and we did the list ranking on the remaining nodes, that we have the correct distances for these remaining nodes. Okay, so now we need to put back the nodes that we removed. Okay, and the way that you put back the nodes that you removed is that if you put back the node I, well then what should his distance be? Well, his distance should be equal to his dist I, right before you remove this node. Okay, this is the distance from I to its next node. And then this distance, after you put I back, right, then the next node has already computed the correct distance from himself to the very end. Okay, so therefore this is the distance of the next node to the end of the list, and this is the distance from this node I to the next node. So therefore, if you add these two together, then you get the correct distance of node I to the end of the list. Okay, so as an example of that, right? So here we took out this fifth node over here. Okay, so when you took him out, he had a distance of 2. Okay, meaning that he was 2 hops away from the next node. Okay, and so when you put this node back, right, then what you're going to do is when you put him back, then this next node has already computed the correct distance to the end. Okay, the correct distance is 3. Right? And when you put this node back, you're going to add the distance to the next node to that node's final correct output, which is 3. Okay, so you're adding 2 and 3, so you get a 5 over here. Okay, and 5 is indeed the distance of this node from the end. Okay, and if you do this another step, right? So if you put in all of these other nodes that we took out, right? Then when you took them out, they had a distance of 1 to the next node. Okay, so for each of these nodes that we put back, we would take this value 1 and then add it to the distance of the next node. So then here you would produce a 6, right? And you would produce a 1 plus 3 is 4 here, and then 2 here. Okay. Yeah, and then so you see that as you unroll this, as you sort of go back through this recursion, then by doing by setting distances this way, then we get all of these correct distances. Okay, so the final thing is to analyze the complexity of this. Okay, so this shows how this shows how the algorithm works and argues why it's correct. Okay, so the final thing is to show that the complexity of the node removal step and the node and putting back the nodes, right? Those two steps do not have high complexity. Okay, have order n work in total. Okay, so the first thing is that as you take out the nodes, okay, so we saw that each time you could find an independent set of size omega n. Okay, so you can take out a constant fraction of the nodes, right? And then we wanted to end up with this number of nodes, with n divided by log n number of nodes. Okay, so you want to remove a log n fraction of the nodes, right? And each time you can remove a constant fraction. So therefore, the number of rounds that you need to run for before you can remove this log n fraction is going to be the log of log n. Okay, so it's going to be double log n rounds until you're down to a set of this size. Okay, and then once this happens, then as I said, after you can apply pointer jumping on this set, and that's going to take you log n time. Okay, so then each round, okay, in order to find these independent sets, okay, this is going to take log n time. Okay, so therefore the total amount of time this is taking is that we need to run this for log n rounds. Each round to find the independent set takes log n time, so the total time is going to be log n times double log n. And it turns out that if you use so there are more efficient techniques where you can actually reduce this value here down to simply log n. Okay, so therefore removing all of these independent nodes, right? In total, that can be done in log n time. Okay, and so restoring all of these nodes can also be done in log n time. Okay, so therefore we can do this in log n time. And the final thing to do is to look at how much work we're doing. Okay, so for the amount of work, what we have is that as you run this algorithm, you have less and less nodes. Okay, and so since you're taking out a constant fraction of the nodes each time, then the number of remaining nodes in the kth round is going to be c to the kth power times n, right? For some c less than 1. Okay, so for example, if you take out a third of the nodes each time, okay, then c here is going to be 2/3, and you're going to have like 2/3 of the k times n number of nodes in the kth round. Okay, so then the the amount of work that's being done in the kth round is simply that each of these remaining nodes is going to do like a constant amount of work. Okay, so therefore the total amount of work being done in the kth round, the total amount of work done in the kth round is equal to c to the k times n. And so the total work done in all the rounds, right? So here we ran for log n rounds. The total work done in all these rounds is going to be just the sum of this stuff, right? For k from 0 to log n. Okay, and so this is a geometric series, and this is going to add up to just linear, okay, to order n. Okay, and the pointer jumping part, right, also has linear work. So therefore, the sum of the work for all of these steps is linear. Okay. Yeah, so therefore we have a work efficient algorithm, linear work algorithm for list ranking, which can be made to run in time log n. Okay. All right. So then in the later lectures, we're going to look at how to solve other problems, and many of them are going to require us to use these list ranking algorithms.